Welcome! In this session, we'll explore the problem KTH missing positive number. This is an exciting challenge that tests your understanding of array manipulation and logical reasoning. Let's dive in and break it down step by step. In this problem, you are given a sorted array called ARR, which contains distinct positive integers, as well as a positive integer k. Your task is to determine the KTH missing positive integer. But what exactly is a missing positive integer? It's any positive number greater than 0 that is not present in the array. Essentially, you need to identify which numbers are skipped in the sequence up to the KTH missing one. For the input format, you'll receive the sorted array ARR and the integer k, and the output will simply be the KTH missing positive integer. Let's look at an example to make this clearer. If ARR is 2, 3, 4, 7, 11, and k is 5, we'll find the fifth missing number in the sequence. The output for this example is 9. Here's why: the integers that are missing from the array are 1, 5, 6, 8, 9, 10. These are the numbers that are skipped in the sequence of all positive integers starting from 1. The fifth missing number in this list is 9, so that is our answer. Now, consider a second example where ARR is 1, 2, 3, 4, and k is 2. In this case, the missing numbers are 5, 6, 7, and the second missing positive integer is 6. By identifying the gaps, we can find the result. Now let's look at another example to further solidify the concept. Suppose ARR is 3, 6, 8, 10, and k is 4. The missing integers here are 1, 2, 4, 5, 7, 9, 11. The fourth missing number in this sequence is 5. This example demonstrates how gaps can occur both before and between the elements of the array. It also highlights that the KTH missing number could appear well before or after the range covered by the values in ARR. To solve the problem, we need to carefully track these gaps and identify the position of the KTH missing number. There are a few constraints and edge cases to keep in mind. First, the length of ARR will range from 1 to 1000, and each number in the array will be between 1 and 10,000. The array is always sorted in strictly increasing order, and k can go up to 1000. Now, for edge cases, if k is larger than the total number of missing integers within the range of the array, you'll need to account for numbers beyond the array's largest value. Similarly, if the array starts with a number greater than 1, the initial missing integers will include values smaller than the first element. To solve this efficiently, it's important to compute gaps between expected and actual values in the array, while also handling cases where the solution lies outside the array's range. To solve this problem, one straightforward way is to use a brute force approach. The idea here is simple: since the array is sorted and contains distinct positive integers, we can start from the number 1 and check each positive integer to see if it's missing from the array. We keep counting the missing numbers until we reach the KTH missing one. The steps involve initializing a pointer to traverse the array and a counter to track how many numbers are missing. For each positive integer, we check if it's in the array. If it is, we move the pointer forward; if it's not, we increment the missing count. Once the missing count matches k, we return the current number. While this method is easy to understand and implement, it has drawbacks. For large values of k, it can become inefficient because we end up iterating through many numbers, making the time complexity n plus k. Furthermore, it requires constant comparisons, which can be time-consuming for bigger inputs. A more efficient solution leverages the sorted property of the array and uses binary search. The idea here is to calculate how many positive integers are missing before each element in the array. This allows us to narrow down the range where the KTH missing number lies without iterating through all numbers. One key observation is that for any element ARR, I, the number of missing integers before it is given by the formula ARR, I plus 1. If this count is less than k, it means the KTH missing number must be after ARR, I, otherwise, it lies before it. Using this insight, we can apply binary search. We initialize two pointers, left and right, to represent the search range. At each step, we calculate the midpoint and determine the number of missing numbers before ARR, mid. Depending on whether this count is less than k, we adjust either the left or right pointer. This process continues until the search range narrows down, and we can calculate the kth missing number using the formula left plus k. The binary search approach is highly efficient due to its logarithmic time complexity, O log n. This is because we repeatedly divide the search range in half, instead of checking each number individually. Additionally, it has a space complexity of O(1), as it only requires a few pointers and does not use any extra space for data structures. This method is particularly advantageous for large arrays or when k is very large, as it avoids the repetitive comparisons of the brute force approach. However, it is slightly more complex to implement, requiring a clear understanding of how the missing count is calculated and how to adjust the search range. Despite this learning curve, the performance benefits make it the more practical choice for most scenarios. The binary search approach is the preferred strategy for this problem because it efficiently utilizes the sorted nature of the array to quickly calculate missing numbers. While the brute force method is intuitive and straightforward, its inefficiency for large inputs makes it less suitable for scalable solutions. The binary search method, on the other hand, offers logarithmic time complexity and constant space usage, making it optimal for both large arrays and large values of k. The key insight, or aha moment, in this approach is the realization that the total number of missing numbers before any index can be calculated using the formula ARR, mid plus 1. This eliminates the need to iterate through all numbers and allows us to directly pinpoint the range where the kth missing number lies. For these reasons, binary search is the best choice, striking a balance between computational efficiency and practical implementation. To solve the problem of finding the kth missing positive integer, we are given a sorted array of distinct positive integers called ARR. Our goal is to determine the kth missing number in the sequence of all positive integers. For instance, if ARR equals 2, 3, 4, 7, 11, and k equals 5, we notice that the missing numbers are 1, 5, 6, 8, 9, and the 5th missing number is 9. To approach this systematically, we can first use a brute force method where we iterate through all positive integers and identify the ones missing from the array. The algorithm starts by initializing a few counters, missing count, which keeps track of how many missing numbers we've encountered so far, current, which represents the positive integer we're currently checking, and index, which helps us traverse through the array ARR. These counters lay the groundwork for our iterative search process. Now, we iterate through all positive integers starting from current equals 1 and continue until we find the kth missing number. For each positive integer, we check if it is less than the current element in the array at position index. If it is, this means the number is missing from the array. In this case, we increment missing count, and if missing count becomes equal to k, we return the current number as our result. On the other hand, if the current number matches the element in the array at position index, it is not missing, and we simply move the index pointer to the next position in the array. Regardless of whether the current number is missing or not, we increment current to check the next positive integer. The process terminates as soon as we find the kth missing number. This approach leverages the fact that the array is sorted, enabling us to track which numbers are missing using the index pointer. While this ensures correctness, it's worth noting that this method is not the most efficient, especially for large values of k, as it involves iterating through many numbers before finding the result. The algorithm primarily uses simple data structures and variables to achieve its goal. The sorted array ARR stores the positive integers already present, while the counters missing count, current, and index help us track missing numbers and the current position in the array. In terms of time complexity, the worst-case scenario involves iterating through all positive integers up to the kth missing number. Since each iteration involves constant time operations, the time complexity is O(k). The space complexity is minimal, as we only use a few variables, making it O(1). Despite its simplicity, this brute force approach has some limitations. For large values of k, the linear search can become slow and inefficient. To address this, we can use an optimized approach based on binary search that takes advantage of the sorted nature of the array. By reducing the number of iterations required, binary search can significantly improve the performance of the algorithm, which we will explore in the following section. This implementation solves the problem of finding the kth missing positive number efficiently. The function findKTH takes two inputs, ARR, a sorted list of distinct positive integers, and k, the index of the missing positive number we want to find. The algorithm initializes two pointers, missing underscore count to keep track of how many missing numbers have been encountered, and current to iterate through all positive integers. The index pointer is used to traverse the input array. The main loop continues until missing underscore count equals k. Inside the loop, we check if the current number is present in the array. If it is, the index pointer is increment to check the next element in the array. If not, it means the current number is missing, so we increment missing underscore count. The current variable is always increment regardless of whether the number is missing or present, ensuring that we eventually reach the kth missing number. When the loop exits, the current variable is one step ahead of the kth missing number due to the final increment. So, we return current 1 as the result. This approach ensures that we count missing numbers efficiently without unnecessary computations. It handles edge cases such as when the array is empty or when the missing number lies beyond the largest number in the array. The time complexity is O, n plus k, where n is the length of the array and k is the index of the missing number. The space complexity is O, 1, since we use only a few variables to track the counts and indices. This is the Java implementation of LeetCode problem number 1539, kth missing positive number. The logic mirrors the provided Python implementation, with the main differences being Java-specific syntax such as explicit type declarations and the use of arrays instead of Python lists. The code uses a while loop to iterate through numbers, checking if they are present in the input array. If a number is missing, it increments the counter for missing numbers. Once the kth missing number is found, the loop exits, and the result is returned. This implementation is efficient and follows standard Java coding conventions. To solve this problem, we start with the array 2, 3, 4, 7, 11, and k equal to 5. First, we initialize three variables, missing underscore count to 0, which keeps track of how many missing numbers we've found so far, current to 1, representing the current number we are checking, and index to 0, which tracks our position in the array. In the first iteration, current is 1, and the first element of the array at index 0 is 2. Since 1 is not in the array, it is a missing number. We increment missing underscore count to 1 and move current to the next number, 2. In the second iteration, current is now 2, which matches the array value at index 0. This means 2 is not missing, so we move index to 1 and current to 3. For the third iteration, current is 3, which also matches the array value at index 1. Again, 3 is not missing, so we move index to 2 and current to 4. Now, in the fourth iteration, current is 4, which matches the array value at index 2. This means 4 is not a missing number, so we move index to 3 and current to 5. In the fifth iteration, current is now 5, which does not match the array value at index 3, which is 7. Therefore, 5 is a missing number. We increment missing underscore count to 2 and move current to 6. In the sixth iteration, current is 6, and the array value at index 3 is still 7. Since 6 is also not in the array, it is another missing number. We increment missing underscore count to 3 and move current to 7. For the seventh iteration, current becomes 7, which matches the array value at index 3. This means 7 is not missing, so we move index to 4 and current to 8. At this point, in the eighth iteration, current is 8, which does not match the array value at index 4, which is 11. This means 8 is a missing number. We increment missing underscore count to 4 and move current to 9. In the ninth iteration, current is 9, and the array value at index 4 is still 11. Since 9 is also not in the array, it is another missing number. We increment missing underscore count to 5, which matches our target value of k. At this point, we exit the loop, and the answer is current 1, which gives us 9. Therefore, the fifth missing positive number is 9. For the second example, we are given the array 1, 3, 6, and k equal to 4. We start with the same initialization, missing underscore count is 0, current is 1, and index is 0. In the first iteration, current is 1, which matches the array value at index 0. This means 1 is not a missing number, so we move index to 1 and current to 2. In the second iteration, current is 2, which does not match the array value at index 1, which is 3. Since 2 is not in the array, it is a missing number. We increment missing underscore count to 1 and move current to 3. In the third iteration, current is 3, which matches the array value at index 1. This means 3 is not missing, so we move index to 2 and current to 4. Continuing, in the fourth iteration, current is 4, which does not match the array value at index 2, which is 6. This means 4 is a missing number. We increment missing underscore count to 2 and move current to 5. In the fifth iteration, current is 5, and the array value at index 2 is still 6. Since 5 is also not in the array, it is another missing number. We increment missing underscore count to 3 and move current to 6. In the sixth iteration, current is now 6, which matches the array value at index 2. This means 6 is not missing, so we move index to 3, which is out of bounds, and current to 7. In the seventh iteration, current is 7, and since index is out of bounds, 7 is a missing number. We increment missing underscore count to 4, which matches k, and move current to 8. At this point, we have found 4 missing numbers, so we exit the loop. The answer is current 1, which is 7. Therefore, the fourth missing positive number is 7. In the third example, we have the array 5, 6, 7, and k equal to 3. Again, we initialize missing underscore count to 0, current to 1, and index to 0. In the first iteration, current is 1, which does not match the array value at index 0, which is 5. Since 1 is not in the array, it is a missing number. We increment missing underscore count to 1 and move current to 2. Next, in the second iteration, current is 2, and the array value at index 0 is still 5. This means 2 is a missing number. We increment missing underscore count to 2 and move current to 3. In the third iteration, current is 3, and the array value at index 0 is still 5. Since 3 is also not in the array, it is another missing number. We increment missing underscore count to 3, which matches k. At this point, we exit the loop, and the answer is current 1, which is 3. Therefore, the third missing positive number is 3. To analyze the time complexity of the algorithm, we start by understanding how the while loop operates. The loop continues until the missing underscore count reaches k, and within each iteration, the current number is increment. The algorithm then checks if the current number matches an element in the array ARR. If it does, the index pointer moves forward, skipping that number. Otherwise, the missing underscore count variable increases to account for a missing positive number. In the worst-case scenario, the loop runs through all numbers from 1 up to k plus len, ARR. This happens when the array contains small values, requiring the algorithm to count many missing numbers after the largest value in ARR. Since each iteration involves constant time operations like comparisons and pointer updates, the overall time complexity is O, k plus n, where n is the length of ARR. In the best case, if k is small relative to the values in ARR, the loop terminates much earlier, but the complexity remains proportional to O, k plus n, with smaller constant factors. Now, turning to space complexity, the algorithm is highly efficient in this regard. It uses only 3 variables, missing underscore count, current, and index, to track the computation's progress. Importantly, it does not rely on any additional data structures to store intermediate results, meaning the space complexity is O(1). When compared to a brute force approach, the difference becomes clear. A naive solution would generate all missing positive numbers in a separate list up to the kth missing value, requiring O, k, space to store these numbers. While both approaches share the same time complexity, O, k plus n, the brute force method is less memory efficient. By avoiding the creation of extra data structures, the optimized algorithm achieves constant space usage, making it much more practical for larger inputs. In summary, the optimized solution stands out for its memory efficiency. Unlike the brute force approach, it avoids creating additional data structures by relying solely on basic variables for tracking the computation. This results in an O(1) space complexity. While both methods share the same time complexity of O, k plus n, the optimized approach is better suited for handling large inputs due to its reduced memory overhead. This makes the algorithm not only faster in terms of memory access but also more scalable for real-world scenarios with larger datasets. When solving this problem, there are a few common pitfalls to watch out for. First, some solutions fail to account for all positive integers. For example, if the array starts at 2, it's easy to overlook that 1 is missing. This mistake happens when we assume the missing number must fall between the smallest and largest numbers in the array. Next, overcomplicating the problem can be another issue. Using advanced data structures like hash maps or sets might seem helpful, but they often increase memory usage unnecessarily. Since the array is sorted, simpler techniques like two-pointers or binary search are usually more efficient. Another important point is the distinct constraint. The fact that all numbers are unique means sorting the array is often redundant, and doing so adds unnecessary computational overhead. Finally, be careful with edge cases. For instance, forgetting to check for missing numbers at the boundaries, like one being missing at the start or a number missing after the largest element, can lead to incorrect results. Now, let's consider the importance of time complexity and how it relates to this problem. For large inputs, brute force solutions with O(n) squared complexity may technically work but will fail to meet performance requirements. This is especially true when the input size can go up to 10 to the power of 5. Always aim for more optimized approaches when dealing with such large constraints. Shifting to an interview context, this problem is a classic example of pattern recognition. It's a variation of missing number problems, which are frequently tested in coding interviews. Leveraging the sorted or distinct properties of the input can simplify your solution significantly. For example, in a sorted array, binary search or in-place methods often provide maximum efficiency with minimal overhead. Also, don't overlook the importance of clarifying edge cases during an interview. Always confirm input constraints with the interviewer, like whether the array can be empty or if it must include the number 1. These clarifications can save you from misinterpreting the problem and losing valuable time. Finally, let's take a look at some related problems and alternative approaches that can help deepen your understanding. Problems like LeetCode 268, LeetCode 448, LeetCode 442, and LeetCode 41 all explore variations of missing or duplicate numbers and are worth practicing. As for alternative approaches, binary search is a great option when the array is sorted. It can achieve O log n time complexity, but you might need to add extra logic to handle gaps in the sequence. Another approach is using a hash set, which simplifies the logic by storing numbers for quick lookups. However, this increases the space complexity to O(n), making it less ideal for space-constrained scenarios. Lastly, cyclic sort is an efficient choice for unsorted arrays, offering O(n) time and O(1) space. The trade-off here is that it modifies the input array, so it's not suitable if the original array must remain intact. Each approach has its strengths and weaknesses, so choose based on the constraints and requirements of the problem you're solving. Great job! To summarize, we covered the problem KTH missing positive number, broke down the brute force approach, and discussed its complexities. Key takeaways include the importance of handling edge cases and combining logical techniques for better efficiency. Thanks for watching, please like and subscribe for more. Keep coding, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!